Hello again. This is Math 2232 coming to you from the College of DuPage. And this is a video lecture for 11-8 as I'm giving my presentation in Springfield. The title of this lecture is Applications of Parametric Representation of Arc Length, Differential, and more. As always, please be attentive listeners while watching this video, taking notes, and pausing the video to work the problems as I suggest. And we are going to start here, as we often do when we have the normal VCM. We're starting with an unquiz. I would allow you 10 minutes to do this, but in this video you could actually take more, and I would encourage you to spend the more time so that you can actually come up with a solution. And so pause the video at the end of my statement here and try the problems. And the directions are, for problems 1 and 2, determine the area of the region below the parametric curve given by the set of parametric equations. In fact, you may want to try to graph these as well. For each problem, you may assume that each curve traces out exactly once from left to right for the given range of t. And for these problems, you should use only the parametric representations to determine the answer. You do not have to try to eliminate the parameter. So problem number 1 is x is equal to 4t cubed minus 4t squared. Y is equal to t to the 4th plus 2t squared. And t runs from 1 to 3. And for number 2, it's x is equal to 3 minus cosine cubed of t. Y is equal to 4 plus sine t. And t runs from 0 to pi. So please give it a go. Let's see how you did. Okay, so number 1, what we're really doing is we put the expression for y here, and we have to do dx, but dx is dx dt times dt. So when we do that, for the x being f of t and y equal g of t, as we talked about, we're integrating then from 1 to 3. That's the values t goes from. This is y, this is t to the 4th plus 2t squared times, this is dx dt, 12t squared minus 2t dt. Now we have to multiply all this out and collect like terms, but we get the integral from 1 to 3 of 12t to the 6th minus 2t5 minus 24t to the 4th minus 4t cubed dt. We do the integrals in all these cases. We're adding 1 to the exponent, dividing by the new exponent, and we're evaluating at 1 and 3, and we get this rational expression. 481,568, all divided by 105. The second problem also, we're really just following the formula. This is what we had for y, and this is the derivative of x with respect to t, and then dt, and we're going from 0 to pi. So we have the area is equal to 4 plus sine t, and this is 3 cosine squared t times sine of t dt. And then we have to distribute this across, and so we get the integral from 0 to pi, 12 cosine squared of t times sine of t plus 3 cosine squared of t sine squared of t dt. So we will go through and integrate this. This is a nice u substitution because when you let u equal cosine, the derivative is essentially sine. There is a minus sign that happens there. And here you get 3, and we can use a trig identity here. And we know that cosine of t times sine of t is 1/2 sine of 2t. So we can substitute that in squared, and that makes this integral doable. It's very difficult trying to do it, the way that we have it, but the trig identity, as always, makes things much better. And so then we square the 1/2, we get 3/4, and that's sine squared of 2t. Now to integrate sine squared, you have to again use a trig identity. The sine squared of 2t is going to be 1 minus cosine of 4t divided again by 2. And so that's the substitution that we're making here. But now we do the u substitution, and we get this as minus 4 cosine cubed now of t The minus comes from doing the substitution here with a minus, and then we get 3 over 8t. And then here we get minus, and we have to do a u substitution here, 3 over 32 sine of 4t. We're evaluating this at pi and 0. Do carefully evaluate this, but when you do, you will get 8 plus 3 over 8 pi. So make sure you can do problems like this. And that concludes our quiz for the day. Now some cockpit commentary. And normally I pause for questions. You can ask questions on the video, but certainly you can ask questions in my office hours, and so you're welcome to do that. Just the cockpit commentary briefly is we are on course and on schedule. You are getting the course that you paid for, and we have much yet to do, but we also have some time. I'll talk about that in the next slide. And today we're going to be doing some problems with respect to arc length and surface areas, and we're going to be doing these in parametric form rather than the way we did them earlier in the course. And as a preview of coming attractions, we're going to be doing very soon polar coordinates, conic sections in polar coordinates, and hyperbolic trigonometric functions, and that pretty much brings us to the end of our course. A little bit of calendar notation. As I promised, this is today. You're watching the video instead because I was invited to give a talk in Springfield, and I'm hoping to make that trip, so I'm making this video for you today. But at the end of this week, we only have a short week here because we only meet once. Even though we're only meeting once, you can do math every day of the week. I will be doing math every day of the week, but we will have one lecture next week, and then, so that's a short 1 week. In fact, it's 1/3 the length of our normal weeks, and then we will have a full week here and another full week here. So you see there are a total of 3 weeks, but one of them is short. And here is our final exam testing window. More about that later and soon. So those of you who are still engaged in the course realize that there's a very big upside opportunity with the comprehensive final exam. So there's still time to catch up. But we're still covering new material, so you want to engage rigorously. Realize this is a 5-hour course. It counts for a lot. It's also a gateway course for Calc 3. Okay, so let's continue with our lecture then. Recall the formula we derived earlier, which was the arc length, but now we're using parametric equations. So we have x of t and y of t, and we learned last time in the lecture that the arc length is the integral from alpha to beta. Now, alpha and beta are the values of t, but then we're integrating now a different formula. It is the square root of dx dt whole squared plus dy dt whole squared. So this is the formula we're going to be using extensively during today's lecture. So let's dive right into it. Determine the length of the parametric curve given by the following parametric equations. X is equal to 3 sine t, y is equal to 3 cosine t, and t runs from 0 to 2 pi. Now, for maximum learning, I'm suggesting here and other places, this is the only place I'm reading it, that you pause the video and give this a try. If you solve it, congratulations. If not, you're better prepared to understand the solution that we go through. So pause the video now. Let's see how you. Well, this is a circle centered at 0, and you go around the circle once, so you actually know a formula for this. But let's use our approach here, our new formula. So we're going to take the derivative dx dt. Here was x, so dx dt is 3 cosine t. Here is y, so dy dt was minus 3 sine t. But then I square both of those and take the square root. Now notice here I get 3, that's the square root of 9, but then I have sine squared t plus cosine squared t, which is known to be 1. So I can jerk the 3 out, and I'm integrating 3 from 0 to 2 pi, and so the answer is going to be 6 pi, which is the same thing that we would have gotten if we were talking about integrating over the circumference of a circle of radius 3. Please make sure you can answer any questions that you have on this. Make sure you make a list of those questions and make sure they're answered. Now, since this was a circle, we were not surprised with the result, but it was nice to see that. Now, here we're going to look at a possible consequences if a curve is traced out more than once, and we try to find the length of the curve without taking this into account. Okay, so here we go. We're talking about using the arc length formula for the following representation, and it looks a lot like what we had before, except instead of having 3 sine t and 3 cosine t, we now have this being 3t. We're still going from 0 to 2 pi. So please give it a go. Let's see how you do. Well, this is the identical circle, but you go around 3 times when you think about it. So the length around the circle is still 6 pi. That should have been pi up there. But you go around 3 times, so that means you trace the circle 3 times. So the derivative here is going to be 9 this time, cosine 3t, and the derivative here is going to be minus 9 sine 3t. Now still, when we put them into the formula, we'll get the square root of 81, which is 9. So you can pull the 9 through, but we'll go around the circle once. This is once, integrating from 0 to 2 pi. So that is 2 pi times 9, or 18 pi. So you went around the circle 3 times. So the answer was 3 times the actual length, and that's because the circle was traced out 3 times. Now, if we had wanted to determine the length of this circle using parametric equations, just going around once, we would realize that when we have cosine and sine of 3t, the period is 2 pi over 3, so we would have only had to go around once, and we've got it 6 pi. Now, be careful not to make the assumption this always will happen if a curve is traced more than once, because sometimes what will happen when a curve is being traced, you will end up with dx dt ending up being not positive but negative, changing signs. So you have to be careful. Just because the curve is traced out n times does not mean the arc length formula will give you n times the actual length of the curve. Let's do another example. Now we want to find, and this is a more complicated thing, we're going to start with a circle of radius 1, but this circle of radius 1 is rolling around the circumference of a larger circle of radius 4. And I do have a picture that I'm going to show you in a moment of this. And back in the day, some of the earlier astronomers actually were using these kind of geometric figures to describe the motion of planets before they figured out that. And in fact, this is called an epicycloid. We talked about the cycloids earlier, traced by a point on the circumference of the smaller circle. Now, we're telling you what the equation is. It is x is equal to 5 cosine t minus cosine 5t, and y is equal to 5 sine t minus sine of 5t. And so the idea is you want to find the distance traveled by the point in one complete trip around the larger circle. It would be instructive for you to think about the graph of this and think if you could actually derive these equations, but that's not what you're being asked to do here. Okay, so please, I'm going to show you the curve, and then I expect you to give it a go. Here's the curve, and you see we're trying to find what is the length of the black curve. And you can see that it goes around as t increases. You can see the orientation. It is going counterclockwise. Let's see how you do. Okay, well, one thing that you want to realize is that there is symmetry. And so if you look at the first quadrant, you really can just go in the first quadrant and multiply by 4 because there is that symmetry. That makes things a lot easier. First of all, you don't have to do all those calculations, and the other thing is you get to go from 0 to pi over 2. But we're using our formula then, so the arc length is 4 times the integral from 0 to pi over 2 dx dt whole squared plus dy dt whole squared dt. And so then I start substituting in what the equations are. I am taking the derivatives each time. So I'm getting this for dx dt whole squared. I'm getting this for dy dt whole squared. And then I have to simplify this. Now when you start doing this, you realize that you do get some places where you have sine squared plus cosine squared, and so you're in good shape with that. And then also when you simplify, you realize that there is an opportunity right here to use the distance formula difference formula, actually not distance formula, difference formula for cosine. And so we use that trig identity here to change this expression here, minus 2 sine t, sine 5t, minus 2 cosine t, cosine 5t, to change that to 2 cosine of 4t. And this then is, we can use the double angle formula to reduce this to being the square root of 4 sine squared 2t dt. And the square root of that is just sine of 2t. And again, this one is easy to integrate. And we will get cosine 2t, we divide by minus 2, and we plug in the endpoints, and we get that this answer is 40. Please make certain you understand this formula. Let's do another problem here. Let's look at something more complicated. This is problem 51. And what we're to do is find the arc length of the curve on the given interval. So we have x is equal to e to the minus cosine t, and this is e to the minus t sine t. These things actually come up quite a bit in differential equations, and we're going from 0 to pi over 2. Please pause the video and give it a go. Let's see how. Okay, well, dx dt, now you do have to use the product rule, but you will get this as dx dt. And then when you do dy dt, again, you'll have to use the product rule, but you will get this. And then you'll square this and square this. Now, it turns out when you substitute those in, you get a lot of cancellation because sine squared of t plus cosine squared of t is 1, and also these things have opposite signs when you start expanding them. And so it is, so there's a minus here and there's a plus here. And so you can do a lot of simplification, and upon the simplification, you'll get having the integral from 0 to pi over 2. This is the square root of 2 e to the minus 2t. You can pull out this constant, and you're integrating this. The integral of e to the minus t is going to be this. You plug in the endpoints, and we get an exact answer, which is what I'll be asking for on the high stakes assessments of, this is the square root of 2 times 1 minus e to the minus pi over 2. And before moving on, we should notice that, again, as we talked about before, arc length can be characterized as s, and we can talk about ds. Now, previously we talked about if we had dx, we get this expression for ds. If we have dy, we get this expression. But now we have another expression, and this is, if there, it is dt, it is this. So we have 3 expressions for ds. And we can use this ds in whenever we're talking about surface area of revolutions. Now what I'm going to do is I'm going to make this video into 2 parts, so I am pausing this video right now. So we're going to be ending the show, and there'll be a part 2. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself, because self-care is important, and take care of each other because we're all in this together. Strive to make a difference each and every day. Thanks for watching. Please take care, and I look forward to seeing you in class soon.